Hello everyone and welcome to Chapter 0, the prerequisite material for the 3-phase induction machine course. In this chapter we are going to cover voltage configurations, force and torque production, review of AC circuits and review of magnetic circuits. So before we start on looking for the outcomes from this chapter, bear in mind that if you need more details for the fundamentals, this is not the chapter you need. That one is just to give you the help or push you in the 3-phase induction mode. So if you are going to start the 3-phase induction mode from scratch, this is suitable for you. But if you need more details about circuit fundamentals, you need another course. So once you finish this chapter, you will understand the principles of voltage and torque production, how to analyze AC circuit, for example, how to solve the 3-phase induction motor equivalent circuit. You need to differentiate between resistive, inductive, and capacitive loads. We need to understand the fundamentals of magnetic circuits and how to calculate the magnetic flux or the self-inductance. So what we are going to cover in this video, we are going to cover voltage configuration, force and torque production.
Let's start by this question. What are the voltage configurations? Or we can ask a question by another way, where we can find the voltage in electrical circuits or electrical systems. Most of the students answered this question that we have DC and AC, which is 100% correct that we have voltage sources, DC sources like batteries, or AC sources like the variac we have in our lab. But also we can find the voltage in electrical circuits, something like this one. We have a drop voltage. If we have a current going through this resistance from left to right in this direction, we have a voltage by this polarity, V equals IR according to Ohm's law. Also, if we have an impedance like this one, Z, something like resistance, inductive reactance, inductive capacitance, we can find that the voltage equals IZ. We notice here that you write the right equation in capital letters, where the left equation is small letters. Any difference? Yes. If we have a capital letter, so we can have DC value. For example, that one is a DC value, but also we can have that one as RMS value or peak value. So if we have a specific value, we are going to write the voltage in capital letters. But if we have a voltage or current or flux function of time, we are going to write it in small letters. So I'm going to rewrite this equation as V of t equals I of t multiplied by Z. So now we know the difference between capital letter and small letter. So capital letter not only DC value, could be RMS, could be peak as well, specific value. Where also we can find the voltages. We have what we call it static voltage, where E of t, induced voltage E, equals minus N divided by dt, where N is the number of turns and phi is the flux in Weber function of time. So that one is the flux phi in Weber, and assume that we have a flux like a sine wave, sine omega t, for example. So that one is omega t, so that one is the phi of t, so the voltage induced will be a cosine function. A good application for that one is the transformer. If we have a primary winding and secondary winding, we feed the primary winding by a voltage source, so there will be a current and there will be a flux linking the secondary winding. There will be induced voltage based on Faraday's law, where E of t equals minus N divided by dt. The minus sign related to Lenz's law, and we're not going to speak about Faraday's law now, but we are going to have here static voltage, where E of t equals minus N divided by dt. Also, we have dynamic voltage. If we have a conductor with certain length L, and there is a linear speed V in meter per second, so that one is in meter, and that one will be meter per second, and that one is the flux density, will be Weber per meter square. We have induced voltage E of t equals BLV, and that one is a dynamic voltage. A good application for that one is the generator. Something like DC generator, synchronous generator. So this will be the starting equation to find the induced voltage in such machines or such generators. Let us focus in this equation, E equals BLV. The original equation is E equals BLV sine theta, where theta is the angle between the velocity and the field, or the flux density B. So if in purpose we put theta 90 degree, we end up by this equation. So if we have a conductor like that one with length L, and we apply a field or the flux density B in this direction, and we try to pull this conductor by a velocity V meter per second in this direction, so we have induced voltage negative positive, as we can see here. And this follows Fleming right hand rule. So if you open your right hand and you apply a flux to your palm, as we can see here, and your thumb follows the direction of the speed V meter per second, so your fingers pointing to the voltage E equals negative positive. And this is like the machine. If we have the machine a conductor like this one, so if we have a conductor here, we try to pull this conductor by V meter per second, and we have a flux density B applied to this conductor, so the conductor will have negative positive E, as we can see here. So all of them are 90 degree apart, right? And that one follows E equals BLV. So now we know how to produce a voltage. What about the force? To calculate the force, we are going to follow the equation F equals LIB, where F is the force in Newton, L is the conductor length in meter, I is the current in ampere, and B is the flux density in Tesla or Weber per meter square. If we have the conductor with length L and we succeeded to push a current in this direction in ampere, and we apply a flux density B in Tesla, we have a force in Newton in this direction. So please note that they are perpendicular to each other. So if we have the conductor we had before and we apply a flux density B here in this direction, and we succeeded to pull this one by a velocity meter per second, and there will be induced voltage E in this direction, and we connect a small resistance here R, so we succeed to push a current I in this resistance. So the current is going from the bottom of the conductor to the top of the conductor, so definitely there will be a force in this direction. And in this case, the force follows the Fleming left hand rule. So if we apply the flux to our palm, as we can see here, and our fingers point to the current direction, so we have a force in our thumb direction. So let's look for this figure. We have our right hand, our left hand. If we apply the flux to our palm here, so that one is the flux density B. So for right hand, if we succeed to push the conductor or to pull the conductor by velocity V meter per second, so the direction of the fingers will be negative positive E, as we can see here. On the other side, if we succeed to push a current in the conductor I, we get a force F in this direction in Newton. So please note that if we have the flux in the same direction, so the fingers are pointing electrical quantities while our thumbs pointing mechanical quantities. So now we know how to produce a voltage, how to produce a force. What about the torque? To calculate the torque, we are going to start from the torque units, Newton meter. So the torque equal force multiplied by distance R. R is the distance from the pivot. Why you use R not L? L is the conductor length, so I don't like to confuse you. So F dot R, and the original equation includes sine the angle between them. But I'm going to assume that the angle between them is 90 degrees, so the torque equals F dot R. So we're going to use an example from our daily life. Most of us did it before. Assume you want to puncture your car and you want to disconnect this tire. So we are going to use this tool. What we call this tool is called wrench spanner. So either you have the forearm or the L shape. Also, you can use nowadays what we call it impact wrench, but I'm going to focus in the explanation for the L shape now. So you are going to put your leg here. So you are going to apply a force something like 5 Newton. And we have the arm length R, either 5 centimeter or 50 centimeter. And that one is applied to the nut here. So you have a torque at this point. So torque equals F dot R, so that one will be 5 multiplied for the first distance 5 centimeter. So that one give you 0.25 Newton meter. If you use 50 centimeter, so that one give you 2.5 Newton meter. Can you imagine that you have the same effort, but you got a torque 0.25 and another time you got a torque 2.5. So the distance R will affect the torque calculation. For example, if we have electric machine and we have a conductor here, we have a certain force, so the radius of the machine will guide your torque. So this means that the torque is affected as well by the physical dimensions of the electrical machines. So I'm going to speak about the torque later in another video, but that one is a starting point for the torque, how to calculate it from the force. So in summary, what we covered in this video, we covered voltage configurations, voltage production, force production, and torque production. What will I watch in the next video? We are going to cover revision material for AC source and AC circuits. See you in the next video.